In the intro mechanics course, we explored the mechanics basically of particles. And if you remember, we started with things like velocity equals, well, it's really a definition, the derivative of the position in time. We defined the linear momentum, P, mass times velocity. And we notice that if the mass is constant, then we can write Newton's second law as a time derivative of the momentum being equal to the force, right, which, so if we think of dp dt, right, we apply it to this, the mass is constant, this is dv by dt, that's mass times acceleration, and that's Newton's second law. And the acceleration, of course, is second derivative of the position in time. And so we're really dealing with a differential equation that an object of mass m obeys this differential equation. And this is a fairly complicated system to solve. And it's just for one particle, so we can imagine how difficult it would be for many particles. And really what this course is about is finding different techniques, new techniques that allow us to deal with understanding the motion of many particles. So as an example here, we can think of, let's say, we give the position vector of a particle. It's as a function of time. So say we have 2t cubed plus t, and this is the x direction, plus 3t to the fourth minus t squared plus 8. That's the y component, minus 12t squared. That's the z component. And let's say we want to find the velocity. Well, we have to do, by definition, the derivative of the position vector in time. This gives us 6t squared plus 1. That's the component in the x direction. And the unit vector isn't changing with time, so there's no time derivative of this quantity. And so we move on to the next term, which is 12t cubed minus 2t. This is the y component, and then we have minus 24t in the z direction. And so we can get the velocity of the particle at different moments in time. If I wanted the momentum, I could just multiply the velocity times m, and that would be let's say we have a mass of 2 kilograms. Let's say we're being specific, 2 kilograms. So I would have to multiply this by 2, and so I would get 12t squared plus 2 I hat plus 24t cubed minus 4t minus 48t k hat. Let's say I wanted the acceleration. Then I would do the derivative of v in t, and that would be the derivative of this. So I would get a 12t I hat plus 36t squared minus 2 j hat minus 24 k hat. And of course I could get the force, and describe the motion completely of this point particle. But we're always dealing with vectors, so we have magnitudes and we have directions, and so you can imagine the complications of dealing with a large collection of particles that have velocities in different directions, v1, v2, and so on. And so we know, as we've seen in the introductory mechanics, that conservation laws are crucial, and so we will move to looking at conservation laws. They allow us to deal with multiple particles, and then we'll look at figuring out quantities that are numbers to understand the dynamics of large systems of particles.